Hey guys, Spider-Derivative Man back talking to you about derivatives of inverse functions. Now here's a question. What's an Asgardian's favorite part of a burrito? The tortillas!
First vocabulary term is a one-to-one function. That's a function for which every element of the range of the function corresponds to exactly one element of the domain. This is also called a monotonic function. So as you can see down here, we have examples of monotonic or one-to-one functions, and that just means that for all of these functions down here, each of the y values correspond to exactly one of the x values, and each of the x values correspond to exactly one of the y values. There's no x value that corresponds to more than one y value. There's no y value that corresponds to more than one x value. In this particular example, for y equals sine of x, notice that we had to restrict its domain. Otherwise, it wouldn't have been considered a one-to-one function. This is only a one-to-one function if we look at sine from negative pi over 2 to pi over 2. Also note that y equals f of x is a function if it passes the vertical line test. We learned this in Algebra 1. Let's say we graph y equals f of x. If we take a vertical line, a vertical straight edge, and move it across the graph of y equals f of x from left to right, and it doesn't touch the graph at two or more points at the same time, then you know y equals f of x must be a function. It's a one-to-one function if it passes both the vertical line test and the horizontal line test. So if it passes the vertical line test, like we just said, and we take a horizontal line or a horizontal straight edge and move it from the top of the graph to the bottom of the graph, and it doesn't touch the function at two or more points, then not only is it a function, but it must be a one-to-one function. Now, an inverse function is a function that undoes the action of another function. A function f inverse is the inverse of a function f if whenever y equals f of x, then x equals f inverse of y. In other words, applying f and then f inverse is the same thing as doing nothing. So basically what this is saying is that a function and its inverse undo each other. Now, in order to find the inverse of a function, all you have to do is switch the x and the y and solve for y. So in this particular instance, we have f of x is equal to 2x plus 8. We just change f of x to y because those two things mean the same thing. If we want to find the inverse of this function, we switch the x and the y, and then we solve for y by subtracting 8 and then dividing both sides by 2. And you get f inverse of x is equal to 1/2 x minus 4. Same thing here. We have our function g of x is equal to x cubed minus 3. If we want the inverse of this function, we just replace g of x with y. We then switch the x and the y, and then we solve for y. And you get g inverse of x is equal to the cube root of x plus 3. Same thing over here. We have h of x is equal to sine of x. If we made this a y, we would have y equals sine of x. We then switch the x and the y, and then you take the inverse sine of both sides, and you get h inverse of x is equal to arc sine of x or inverse sine of x. These two things mean the same thing. Also note that if f is a one-to-one or monotonic function, its inverse must also be a function. And that makes sense because if it passes the vertical line test and the horizontal line test, then the inverse must also be a function as well. Now let's talk about continuity and differentiability of inverse functions. So let f be a function whose domain is an interval I. If f has an inverse function, then the following statements are true. 1. If f is continuous on its domain, then f inverse is continuous on its domain. And 2. If f is differentiable on an interval containing c and f prime of c equals 0, then f inverse is differentiable at f of c. So this is just some common sense stuff. The first one is just saying if your function is continuous, then the inverse of that function must also be continuous. Part 2 is just saying if you can take the derivative of your function at a particular x value that we're calling c, and that derivative is not 0, then the inverse of your function you could also take the derivative of at f of c. So the y value of the function when you plug in c over here. Now the derivative of an inverse function says let f be a function that is differentiable on an interval I. If f has an inverse function, f inverse, then f is differentiable at any x for which f prime of f inverse is not equal to 0. Moreover, f inverse prime of x is equal to 1 over f prime of f inverse of x, where f prime of f inverse of x does not equal 0. Now, it makes sense why f prime of f inverse of x cannot equal 0, because you can't have 0 in your denominator. But let's explain everything else. So we're starting with a function f, and we want to take the derivative of the inverse of f. So the derivative of the inverse of f of x is equal to 1 over f prime, the derivative of your function, of f inverse of x. So your inverse function, you're going to plug in to the derivative of your original function, f, and it's 1 over all of that. Now, this is a formula that you need to memorize. This is the derivative of an inverse function. This comes up all the time on the AP test. You need to memorize this formula. Now, here are some other formulas you need to memorize. So these are the derivatives of inverse trig functions, and we have arc sine, arc cosine, arc tan, arc cosecant, arc secant, and arc cotangent. And hopefully you already know that arc sine is the same as inverse sine. Arc cosine is the same as inverse cosine, and that's the same for all of these. Also, we are letting u be a differentiable function. So instead of putting x in here, we're putting u, because it's not always just going to ask you what's the derivative of the inverse sine of x. It's going to ask you what's the derivative of the inverse sine of x cubed, or x squared plus 5x. That's what it's usually going to ask you. And so these formulas help you when you're not just taking the derivative of inverse sine of x. So let's pretend real quick that you're taking the derivative of arc sine of x squared, or the derivative of inverse sine of x squared. How that works with your formula over here is up here you have u prime. Well, u, remember, we said is x squared. So what's the derivative of x squared? That's going to be 2x. So in our numerator, we're going to write 2x. And then it's going to be over the square root of 1 minus x squared squared, or x to the 4th. So the derivative of arc sine of x squared, or the derivative of inverse sine of x squared, is going to be 2x over rad 1 minus x to the 4th. That's how you use these formulas, okay? So memorize these formulas.
Example time!
Now, example 1 says verify that f has an inverse. Then use the function f and the given real number a to find f inverse prime of a. So we are given a function and we're given an x value a. And we want to find f inverse prime at x is equal to 3. So here's how this works. These type of problems have 4 steps that I need you to get through. The first step is to verify that f has an inverse. So the way you do that is you graph this particular function. And you see, is it a 1-to-1 function? And yes, this particular function is 1-to-1. It passes both the vertical line test and the horizontal line test. So it does have an inverse function. Step 2 then is to find out what value of x causes f of x to equal 3. You need to figure out what value of x causes your function to equal your particular a value. Now, follow me here. We are finding f inverse prime of a. That means, based on our formula for the derivative of the inverse, we need to figure out what f inverse of a is. Meaning that we need to figure out what value of x causes f of x to equal a. So in this case, we need to figure out what value of x causes f of x to equal 3. We can then work from there. So we set our function equal to 3. How do we figure out where this function equals 3? Well, there's a couple ways. You could guess and check, you could use the rational root theorem, or what I would do is in your graphing calculator, I would graph this function, and then another function I would graph is y is equal to 3. And then I can figure out where those intersect. And that x value is where this function equals 3. And that x value is 2. If I plug in 2 to this function, I get 3. Therefore, this function equals 3 at x is equal to 2. So f of 2 is equal to 3. Now, why is that important? Because in step 3, what we're going to do is we are going to switch the x and the y for f inverse. So if I know that f of 2 equals 3, I know f inverse of 3 must equal 2. I switched the x and the y. So again, I figured out what value of x causes my function to equal this a value. Because in step 3 then, I could switch those and I can get what f inverse of my a value is equal. Why does that help? Because in step 4, we're going to use the formula for the derivative of the inverse, which is 1 over f prime of f inverse of x. And in this case, we are finding f inverse prime of 3. So f inverse prime of 3, that means I'm going to plug in 3 here and here. So how do I simplify this? What is f inverse of 3? That's what I found in step 3. F inverse of 3 is 2, so I can plug in 2 for that. Now all I have to do is find the derivative of my function and then plug in 2. So what is the derivative of my original function? Well, I use the power rule here. I bring the 3 out front. That becomes x to the second power, so it's going to be 3/4 x to the second plus 1 minus 0. So this is my derivative. I then evaluate my derivative at x is equal to 2. That's what what this wants me to do. And I leave that in my denominator. It's going to be 1 over 4. That is what f inverse prime of 3 is equal to. That's how this works. Follow each of the 4 steps and you'll be fine.
You try!
Okay, doing the same thing here. So we start with step 1. Does this function have an inverse? So I graph this function and it is 1 to 1. Therefore, it does have an inverse function. So then I can move on to step 2, which is to figure out what x value causes my function to equal this particular a value. What value of x causes f of x, my function, to equal 7? Well, I set this function equal to 7, and this one, I don't have to graph. I can actually solve this out. So I can subtract 5 on both sides, divide both sides by -2, and cube root both sides. And when I do that, I get x is equal to -1. That means that f of -1 is equal to 7. Now, why does that help? Because in step 3, what I can do is switch the x and the y and make it f inverse. So it's going to be f inverse of 7 is actually equal to -1. And again, why does that matter? Because in step 4, I'm using the derivative of the inverse formula, and I'm finding f inverse prime of x, or in this case, f inverse prime of a, which is 7. So I'm going to plug in 7 here and here. Now, what is f inverse of 7? We just figured out it's -1. So I'm going to plug in -1 for f inverse of 7. I can then simplify this by just finding the derivative of my original function and plugging in -1 for x. So what is the derivative of my original function? Well, here, this is 0. This over here, I use the power rule, becomes -2 times 3 times x to the second. So it's going to be -6 x to the second. So then I take this, plug it in here, and plug in -1 for my x value. -1 squared is 1 times -6 is going to be -6. Therefore, f inverse prime of 7 is equal to -1/6. And you're done. Now, example 2 says, show that the slopes of the graphs of f and f inverse are reciprocals at the given points. So all we're going to do here is verify that these two functions right here, this function and its inverse, have perpendicular slopes at these two given points. So let's first find the derivative of each of these functions. So the derivative of f of x, we're just going to use the power rule. It's going to be 3x to the second power. The derivative of the inverse of x, well, this function is the cube root of x, so we're just going to rewrite that as x to the 1/3 power. So when I take the derivative here using the power rule, it's going to be 1/3 x to the -2/3 power. Now what I can do is plug in my x values for each of these points to these given derivatives and find the slope of my original functions at these given points. So I'm going to plug in 2 for my x value. 2 squared is 4 times 3 is 12. Over here, I'm going to plug in 8 for my x value. Now when I evaluate this, I get 1 over 8 to the 2/3 power. 2/3 power just means I cube root 8, which is going to be 2, and then I square it, so it's going to be 4. So 1 over 3 times 1 over 4 is going to be 1 over 12. Now, are these slopes reciprocals of one another? Yeah, 12 is the reciprocal of 1 over 12. So we have verified this. We've done our job. Good work.
Spider-Man, Spider-Man. You try!
Okay, doing the same thing here, we have our function and its inverse, and we want to verify that the slopes of each of these functions at these given points are reciprocals. So let's first find the derivative of each function and then plug in the given point to those derivatives to get the slope. So we start with our first function. To get the derivative here, I need to rewrite this square root as a 1/2 exponent. Then I can take the derivative, so it becomes 1/2 x minus 1 to the -1/2 power. And technically, you also have to do the chain rule. You have to multiply by the derivative of x minus 9. But since the derivative of x minus 9 is just 1, it doesn't really affect the problem at all. So we just leave our derivative as 1/2 times x minus 9 to the -1/2 power. Doing the same thing for our inverse function. We take the derivative here, and the derivative of x squared plus 9, derivative of x squared is going to be 2x, the derivative of 9 is going to be 0, so that's the derivative of our inverse function. We then plug in these given points to their derivative. So I'm going to plug in 10 for x here. 10 minus 9 gives me 1. 1 to the -1/2 power is still 1 times 1/2 is going to be 1/2. Over here, I plug in 1 for x, and 1 times 2 just gives me 2. Are these slopes reciprocals of one another? Yes, they are. So we have shown that the slopes of each of these inverse functions are reciprocals at these given points. Now, example 3, we're just finding the derivatives of these inverse trig functions. So I'm going to show you how to use these. It's actually pretty easy. So we know the formula for the derivative of arc sine, or the inverse sine of some function, u, is going to be u prime over rad 1 minus u squared. Now, how does this work? again, u is just whatever you're taking the arc sine of, or the inverse sine of. So our u in this case is going to be 2x. U prime means I'm taking the derivative of my 2x. So in the numerator, it's going to be the derivative of 2x, and that's going to be all over the square root of 1 minus 2x squared. Up here, what's the derivative of 2x? That's just 2 times 1, so that's going to be 2. Down here, 2x squared, you square the 2 and the x, and you get 1 minus 4x squared. And that's all you have to do. Done. Let's try B, doing the same thing, except this time we're taking the arcsecant of e to the 2x. So if I want to take the derivative of this, what I'm going to do is use the formula for the derivative of arcsecant, or inverse secant. Now, my u is going to be e to the 2x in this case. So in my numerator, I'm taking the derivative of e to the 2x. Down here, I'm going to plug in e to the 2x for u, and then I'm going to plug in e to the 2x for u here as well. Now, what is the derivative of e to the 2x? Well, derivative of e to the anything is just e to that same anything times the derivative of that anything, the derivative of that exponent by the chain rule. So derivative of e to the 2x is going to be e to the 2x times the derivative of 2x, which is just 2. So 2 e to the 2x is going to be my numerator. In my denominator, I have this e to the 2x being squared. So a power to a power, you just multiply those, you get e to the 4x. Now you can see we have an e to the 2x in the numerator and an e to the 2x in the denominator that we can actually just cancel out, and we end up getting the derivative of arcsecant of e to the 2x is 2 over rad e to the 4x minus 1.
Neutron!
Okay, doing the same thing here. So again, we just need the derivative of arctan of 3x this time. So we need the formula for the derivative of arctan, or inverse tangent. That would be u prime over 1 plus u squared. So what is my u in this case? It's just whatever you're taking the arctan of, or inverse tan of. That would be 3x. So the derivative of 3x is going to go in my numerator, and that's going to be all over 1 plus the quantity 3x squared. Now, what's the derivative of 3x? That's going to be 3 times 1, so just 3. And then what's 3x squared? You square the 3 and the x, and you get 9x squared. And you're done. Over here, you're taking the derivative of arc sine of rad x. Now, anytime you take the derivative and you have a radical, you just want to replace that with a rational exponent. So the square root is the same as the 1/2 power. Now, we're going to use the derivative formula for arc sine. What is that? That's just u prime over rad 1 minus u squared. Now, what is my u in this case? That's x to the 1/2. So in my numerator, I'm taking the derivative of x to the 1/2. I'm then also plugging in x to the 1/2 in my denominator down here for this u. Up here, the derivative of x to the 1/2 power is going to be 1/2 x to the negative 1/2 power. Down here, you have a power to a power, so you just multiply those. What's 2 times a half? That's just 1, so it's going to be 1 minus x. Now, how can I simplify this? Well, I can actually take this x to the negative 1/2 power and bring it down so it's with this 2 down here, so it's going to be 1 over 2x to the positive 1/2 power. Now, what's the 1/2 power? That's the square root. So I can rewrite this as 1 over 2 rad x divided by rad 1 minus x. Now, why do I write it like this? Because you can see the way you're going to simplify this is instead of dividing by rad 1 minus x, I'm going to multiply by the reciprocal. Now you can see we're just going to multiply together these denominators. And how does this simplify? Well, this has a radical and this has a radical. So we can actually multiply these together. I'm going to distribute this x to the 1 and to the x over here. So it's going to be 1 over 2 rad x minus x squared. And you're done. Now, example 4, we are verifying f has an inverse, then we're going to use f and the given real number a to find f inverse prime of a. So it's the same thing we were doing earlier, except this time we have trig functions. Remember, there were 4 steps here. The first step is to figure out, does f have an inverse? Well, is this function 1 to 1? Well, normally sine of x is not 1 to 1. Unless its domain is restricted, which in this case it is. So here we are restricted from negative pi over 2 to pi over 2, which means on that given interval, sine of x is 1 to 1. Therefore, it does have an inverse function. Now, what value of x causes f of x to equal 1/2? If you recall, our step 2 in our previous examples, we needed to figure out where does our function equal our a value. The reason we do that is because in step 3, we're going to switch them and say f inverse of a is equal to whatever x value we find here, and then we can use that in the derivative of the inverse formula. So we set our function sine of x equal to our a value, and we solve for x. So how do I solve for x? Well, I take the inverse sine or arc sine of both sides. Now, what is the arc sine or inverse sine of 1/2? Well, remember, our domain is restricted from negative pi over 2 to pi over 2. So we look at our unit circle. What angle measure has a sine of 1/2? That's what this is asking. that angle is going to be pi over 6. So when x equals pi over 6, we know that our function is equal to 1/2. So we're going to take this, f of pi over 6 equals 1/2, and we're going to use this in step 3, where we switch the x and the y for our f inverse, for the inverse function. So we say if f of pi over 6 equals 1/2, then f inverse of 1/2 is equal to pi over 6. Now what we can do in step 4 is use the derivative of the inverse formula, which looks like this. We are trying to find f inverse prime of 1/2. So we're going to plug in 1/2 here and here for x. We then can simplify this because f inverse of 1/2, we just figured out what that is. That was what step 2 and step 3 were for. It's pi over 6. So we're going to plug in pi over 6 here. We then figure out what is f prime of pi over 6. Well, what's the derivative of our function? Derivative of sine is cosine. So we just have to figure out what is cosine of pi over 6. And cosine of pi over 6 is rad 3 over 2. Now 1 over rad 3 over 2, we have to simplify, and we get 2 over rad 3. Now we don't want to leave a radical in the denominator, so we multiply the numerator and denominator by rad 3, and we get f inverse prime of 1/2 is 2 rad 3 over 3.
Thanos is a big purple idiot. You try.
Okay, doing the same thing here. Remember, there are 4 steps. The first step is, does f have an inverse? So is this function 1-to-1? Well, normally cosine is not 1-to-1, but its domain is restricted on this given interval. Therefore, this function is 1-to-1 on this given interval. So it does have an inverse function. Next, in step 2, we are going to take our function and set it equal to our a value here. The reason for that is we need what f inverse of a is. Therefore, we need to figure out what x value causes f of x to equal a. So then we can switch them in step 3. So we take this a value, 1, and we set it equal to our function, cosine of 2x, and we solve for x. So how do I solve this? I take the arc cosine, or inverse cosine of both sides. What's the inverse cosine of 1? Well, remember, that's just going to be 0. Then we divide both sides by 2, and we get x is equal to 0. This means that at x is equal to 0, this function is equal to 1. So f of 0 equals 1, we take that into step 3, where we take f of 0 equals 1, and we switch the x and the y, and instead make it f inverse of 1 equals 0. Now, the whole reason we did this is because in step 4, we're going to use the derivative of the inverse formula, 1 over f prime of f inverse of x. And we're going to plug in 1 for our x's here. And when we do that, what happens is f inverse of 1, we just figured out is 0. So we can substitute in 0 for f inverse of 1. Now all we have to do is figure out what 1 over f prime of 0 is. What's f prime? That's the derivative of this function here. What's the derivative of cosine of 2x? Well, remember, we have a function within a function, so this requires a chain rule. What's the derivative of cosine? That's negative sine. So it's going to be negative sine of 2x times the derivative of 2x, which is going to be 2. So negative 2 sine of 2x is the derivative of cosine of 2x. We then take this and evaluate it at 0. So we plug in 0 for x. We simplify. 2 times 0 is 0. Sine of 0 is 0. And then 1 over 0, oh, that's undefined. So we know that f inverse prime of 1 must be undefined. Now example 5 says find the equation of the tangent line to the graph of f at the given point. Use a graphing utility to graph the function and its tangent line at the point. So here we are given a function, and we want to find the equation of the tangent line to this function at this given point. Well, in order to find the equation of a line, all we need is a point and a slope. We already have a point, we just need to find the slope of this function at this given point. Well, how do you find the slope of a function? Oh, you take the derivative of that function, because remember, the derivative of a function at a particular point is the same thing as the slope of the function at that point, which is the same thing as the instantaneous rate of change of the function at that given point. It's the same as the slope of the tangent line to this function at this given point. So that's what we're going to do. We're going to take the derivative of arctan of x. Now, what is the derivative of arctan of x? Well, we have a formula for that. The derivative of arctan of u is u prime over 1 plus u squared, where u is whatever we're taking the arctan of. In this case, that would be x. So what's the derivative of x? That goes in the numerator. That's just 1. So it's going to be 1 over 1 plus u squared, which in this case is just x, so 1 plus x squared. That is the derivative of arctan of x. Now, since we found the derivative of our function, we can get the slope of the function, or the slope of the tangent line to the function, function at this given point if we plug in the x value for our point into this derivative. So we're going to take -1, plug it in for x. -1 squared is 1, 1 plus 1 is 2, so it's 1 over 2. That is the slope of this function at this given point. That is the slope of the tangent line to this function at this given point. That's what we're trying to find. Since we have the slope of the tangent line to the function at this given point, and we have the point of tangency, we can create the equation of the tangent line. We just need our slope and our point, and we plug those into point-slope form. So 1/2 goes in for my m, -1 goes in for my x sub 1, negative pi over 4 goes in for my y sub 1. I then simplify y minus negative pi over 4, same thing as y plus pi over 4. Over here, same thing, x minus -1, same thing as x plus 1, distribute the 1/2. You get something that looks like this. Now, if we want to get it y equals, we just subtract pi over 4 from both sides, and I'm okay if you leave it like this. The AP test is okay if you leave it like this. You don't have to simplify these two fractions right here. We confirm this with our graphing calculator. You can see our arctan curve right here and our tangent line. They meet up right at x is equal to -1. Perfect.
If you're wondering why my thumb is visible, it's because I couldn't press play or pause on the phone without cutting a hole in it. You try!
Okay, doing the same thing here. So in order to find the equation of the tangent line, we need a slope and we need a point. We already have our point, so we just need this slope. So we're going to take the derivative and plug in this point. To find the slope, we take the derivative. What is the derivative of arc sine of 3x? Remember, the derivative of arc sine is going to be u prime over rad 1 minus u squared. Now, what is u? U in this case is whatever you're taking the arc sine of, so that would be 3x. So u prime then is the derivative of 3x, which would be 3. And then in our denominator, we plug in 3x for this u, and you have to square the 3 and the x, you get 9x squared. Perfect, we found the derivative. Now we need to plug in our point to find the slope of our function, the slope of the tangent line at this given point. So we take rad 2 over 6, we plug it in for our x here, and then we simplify it. Rad 2 over 6, we square that. You square the numerator and denominator. Rad 2 squared is just going to be 2. 6 squared is going to be 36. You then multiply that to 9, and you get 1/2. What we do then is we subtract these two. 1 minus 1/2 is going to be 1/2. And the square root of 1/2, you square it the numerator and the denominator, and you just get 1 over rad 2. Now, to simplify this is the same thing as 3 divided by 1 over rad 2, which is the same thing as 3 times rad 2 over 1, multiplying by the reciprocal. So you get 3 rad 2. That is the slope of our given function at this given point. It's also the slope of the tangent line to this graph at this given point. So, to write the equation of the tangent line to this graph at this point, we need our slope and we need our point, and we just plug them into point slope form. So I take 3 rad 2, plug it in for my m, take rad 2 over 6, plug it in for my x sub 1, take pi over 4, plug it in for my y sub 1. I can then simplify by just distributing this 3 rad 2 to the x and to the rad 2 over 6. We then add pi over 4 to both sides, and we end up getting our tangent line equation. You can confirm this with your graphing calculator. You can see this curve in here. It's really hard to see, but we do have a curve and we do have our tangent line, and they do meet up at rad 2 over 6.